The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let us start. So first, let me remind you what we did at the end of last lecture. So we considered a large M matrix field theory. And then we saw that when you, when you write down your Feynman diagrams to calculate things, then there's a difference now between the order of contractions, which is now reflected whether you have planar diagram or non-planar diagram, etc. And that in turn also affects your n-counting. So at the end, we discussed two observations. One observation is that for the examples we considered, the non-planar diagram, even though cannot be drawn on the plane without crossing lines, can actually be drawn on the torus without crossing lines. Okay, so the diagram can actually be straightened out on the torus. And the other observation is that the power of n is related to the number of faces you have in your diagram after you have straightened it out. Okay? So in this lecture, I'm going to, now I'm going to generalize these two observations. Okay? So first I will tell you a fact. So many of you may already know this. So first tell you a fact that any orientable two-dimensional surfaces is classified topologically by an integer, which I will call it h. So this h is typically called a genus. Okay. So heuristically, this genus is equal to the number of holes a surface has. Okay. So for example, if you have a plane, so the plane topologically is actually equivalent to a sphere. So when I draw a sphere, that means a plane, because if you identify the point on the plane at infinity, then that becomes a sphere. So topologically, plane is no different from a sphere. So this is a genus 0. So this is plane. So h equal to 0. Okay? And then for the torus, then there's one hole, then this is genus 1. So this is torus. Okay? You can also draw surfaces with as many holes as you want. Say this is a surface with 2 holes. Okay? Surface with 2 holes. And so this is genus 2. Okay? So the remarkable thing is that this actually classifies the topology of all two-dimensional surfaces. Okay? And there's a so-called topological invariant. There's a topological number, so-called Euler number, which is defined to be chi equal to 2 minus 2h. Okay? So h labels the topology, and so the chi is related to h this way. So any surface with the same topology, any two surfaces with the same topology will have the same chi, because they will have the same h. They have the same chi. So chi is what we call the topological invariant. Okay. So this is just a mathematical fact. So now I'm going to make two claims. So these two claims are in some sense self-evident after you have studied a little bit. And so I'm not going to prove it here. We'll just make the claim, and then I will leave the task of to familiarize these two claims to yourself. Okay. But as I said, these two claims is actually self-evident if you just do a little bit study. So the claim one. So this is regarding the structure of Feynman diagrams. So remember the theory, the example theory we considered last time was something like this. Okay. Which phi is a Hermitian matrix. So now the claim. So if you can look at the Feynman diagrams of this series, okay. So the claim is the following: for any non-planar diagram, there exists an integer h so that the diagram can be straightened out straightened out means just made non-crossing, okay? On the genus H surface. But not on the surface with a smaller genus. Okay. So actually, you can classify all the non-planar diagrams by drawing it on some genus H surface, on two-dimensional surfaces with non-trivial topology. And then you should be able to find the number H, which is the lowest genus you need to make this diagram to be non-crossing, okay, non-self-crossing. Last time we saw an example which you can straighten it out on the torus. But with more complicated diagrams, then torus will not be enough. You will need, say, a genus 2 surface or higher genus surface. But I hope this is so you can easily convince yourself that this is doable. Just by some practice. Yeah, also this is very reasonable. Do you have any questions regarding this claim? Good. So this is claim 1. The claim 2 And this is a generalization of the second observation. So claim 1 is the generalization of the first observation of last time. And the claim 2 will be the generalization of the second observation. For any non-planar diagram, just for any diagram, the power of n coming from contracting propagators is given by the number of faces on such a genus H surface. Okay? So the number of, as we explained last time, the number of faces just means the number of disconnected region in the diagram. So once you have straightened it out, then you can, this unambiguous way, you can count the number of disconnected regions in the diagram. And then that number is the number of n. It's the power of n come from the contracting propagators. So this claim is also self-evident because each power of n comes from a single connected line. And essentially, a single connected line will encircle some face. And so the number of independent such face, of course, just the number of power n. Okay? Any questions regarding the second claim? Good. Okay, so based on these two claims, okay, then I can immediately write down the n dependence. Okay? So from this claim, we find a vacuum diagram. Again, we have been only talking about the vacuum diagram. Vacuum diagram is the diagram with no external legs. Has the following dependence. So from here, we immediately conclude that the vacuum diagram has the following G square and n dependence. Okay, so G square is just the coupling constant. So remember, each propagator is proportional to G square, and each vertex is 1 over G square. Okay, just from there. So let's just take arbitrary vacuum diagram. Let me call its amplitude to be A. Then A should be proportional to G square to the power E. Okay, E should be the number of propagators. Because each propagator gives you a factor of G square. Okay? And also matters V, and the V is the number of vertices, denote the number of vertices. And each vertex gives you 1 over G square, so that should give you E minus V. Okay? And then we just multiply n to the power f, and f is the number of faces. Okay. So without doing any calculation, so this essentially characterizes the n dependence, the n and g and the coupling dependence of any diagrams. Okay? Now, if you look at this expression, you say we are doomed. Because this kind of expression does not have a sensible Lagrangian limit. So remember our goal, the original goal of 't Hooft, is that you treat this n as a parameter, and then you want to take n to be large, and then you do expansion in 1 over n. Do expansion in 1 over n means you are expanding around n equal to infinity. Okay, you want to expand around n equal to infinity. But if you look at this expression, n go to infinity is not a well-defined limit. Because I can draw a complicated Feynman diagram which f can be as large as possible. So you just have sufficiently many vertices and sufficiently many propagators, the f is unbounded. So then there's not a well-defined n go to infinity limit. Okay? So this expression, there's no sensible n go to infinity limit. If you don't have sensible n go to infinity limit, then you cannot talk about doing 1 over n expansion, and you cannot even define the limit. It's just done, just finished. Okay? Yes?
But I remember people do partial sum to, can they do the same trick here? Put the large in the denominator, partial sum for a series of similar bubbles, and
Yeah.
like a random phase approximation.
Yes.
Somehow they can infinite sum over infinite number of a and put large n into like a 1 minus n something, put into denominator. It's
Yeah. So people certainly have been talking about Lagrangian expansion. And certainly, if this just failed here, we will not be talking about this. I'm just setting up. I'm just setting up a goal. I'm just setting up a target, which I'm going to shoot it down. Right. Yeah, I mean, just say, if your goal is to do the Lagrangian expansion, this might be a place which turns you back. Okay, you say, there's no Lagrangian limits, and let's find another problem. But 't Hooft is a low ordinary person. And so remember, there are several nice mathematical tricks you have to go through. First, you have to invent this double line notation so that you can count n very easily. Yeah, first you have to come up with this Lagrangian idea. I think it may not due to him. Maybe other people already consider similar things like Lagrangian. But first you have to think about the double line notation to make your computation easier. And then even after you reach this step, and then you need to know this kind of topology, etc. Then after you reach this step, still there's a roadblock here. But 't Hooft find a very simple way to go around it. He say, let not me consider, because when I say this limit is not well defined, I made an implicit assumption. I made the assumption that when I go to infinity limit, the g is kept fixed. Okay? But so that's the reason. Say if you have then this will blow up. But then 't Hooft come up with a different limit. He said, let me consider n goes to infinity, but at the same time consider g squared goes to 0. Okay? At the same time consider g squared goes to 0. Yeah, because the problem of this is that if you have a diagram with lots of faces, and and if you multiply by a finite number, and then, if you take g equal to 0, then you have infinity. Infinity multiply something potentially goes to 0, maybe you will get something finite, okay? 1 second. So you said, let's consider this limit, but so that the product of them is kept finite. Okay, let's consider this limit. So in this limit, then the n counting will be different. So this a will be g squared n e minus l. Yes, because we want to keep this fixed. So we put the m factor here, then we take the m factor out. Then n plus f plus v minus e. Okay? And then let me just write it slightly differently. So this is lambda, if I use this notation, lambda. Lambda now is finite. So this is e minus v. So let me just write it as lambda l minus 1 n to the power chi. So now let me explain my notation. First, L is equal to e minus v plus 1. Okay, it's the number of loops in the diagram. So do you guys remember this formula? Why this is true? Yeah, the reason this is true is very easy to understand. So if you look at the Feynman diagram, the number of loops is exactly the same as the number of undetermined momentum. Okay? So, and each edge, each propagator will carry momentum. And at each vertex, you have momentum conservation. But then there's overall momentum conservation, which is guaranteed. So, so the number of independent momentum just e minus v, and then plus 1. Yeah, it just e minus v minus 1. Okay? Because there's only v minus 1 independent momentum constraint. So this is the number of independent momenta. And so this is the number of loops. And the chi is just defined to be the number of faces plus of number of vertices minus number of edge. Okay? Yes?
Is there any, like, in general, is there a relation between EV and F? Like, are they completely independent of each other?
EV and F?
Yeah.
Yeah, that's what I'm going to explain.
Oh.
Yeah. Any other questions? Did you have?
So the reason that we can't take the m to infinity limit without taking g to 0, is that why we can't apply this to QCD to get a?
No, in QCD we apply this.
But in QCD, g is not small.
It doesn't matter. It doesn't matter. So this is an expansion scheme, and this is expansion scheme, and then it's you can apply to QCD. Then you can ask whether this particular expansion scheme is a good approximation or not. That's a separate question. And for QCD, it's pretty good. It's not that bad. Yeah. Yeah, for QCD, g squared n is finite.
But it's like 10.
No, here does not tell you a lambda have to be small. Lambda can be very big here. It just tells you the lambda in this limit have to be finite.
Okay.
Lambda can be 10 billion, and it can be very big. And actually, in the future, we will take lambda go to infinity. Good. So now, in order to have a well-defined limit, still depends on this chi. So now you ask why this works, because we still have this chi. We still have this chi. But now, again, we need another piece of mathematics. Now we need another piece of mathematics. First, when you draw, let me remind you this two diagram some diagram we had last time. So this is the simplest diagram, and there's another non-planar diagram which you can draw on the torus. okay, which is non-planar version of this, etc. And you can also have more complicated diagrams. Say, suppose you're on the torus, I can consider more complicated diagrams like that. For example, such kind of diagrams, okay? So if you think about such diagrams, then in a sense, each Feynman diagram can be considered as a partition of the surface. So if you draw a diagram on the surface of the surface, a particular surface into polygons. Okay? Yeah, it's very clear here. I can just I draw those non-wave lines, just make them straight, and this one topologically I can just draw like this, and then I have one and the other part. Okay, similarly here. Okay, so essentially, so each Feynman diagram can be considered as you just partition whatever surface you draw the diagram. Is this clear to you? So this is a very important point. Yes. Yeah. Look at this diagram. So this is the Feynman diagram drawn on the torus. Does this look like a partition of torus into polygons? Yeah. So that's what I'm talking about. And the statement that this should apply for any Feynman diagrams. Yeah. So this is like a partition of a sphere. We separate into sphere into 3 regions: 1, 2, 3. Yeah. Yeah. Okay. Any question about this thing? Yes. Do you have a question?
Yeah. Wait, but in that case, the third one isn't bounded, is it? The third.
The third is bounded. I mean, say we should view the plane as a sphere.
Oh, okay. Okay.
Yeah. Topologically, it's the same as a sphere. So now once you recognize this, now you can use a famous theorem due to Euler. Some of you could have learned it in high school, generally in high school, because so this is a theorem. Given a surface composed of polygons, so if you're not familiar with this, you can go to Wikipedia. With F faces, E edges, and V vertices. Okay. Suppose you have a surface like this, and then this particular combination chi, which is defined to be F plus V minus E, is precisely equal to 2 minus H. Okay. So this is why this is called Euler's number. And they only depend on the topology. So this combination only depends on the topology of that surface and nothing else. So we can imagine Tou Hu was a very good high school student, so he already knew this. So now we can rewrite this in as A in script A, lambda to the power L minus 1 n to the power 2 minus 2h. So remember, h is greater than 0. So now this expression have a well-defined limit. Okay? So now these have a well-defined Lagrangian limit. So to the leading order, and in particular, this n dependence only depends on the topology of the diagram. Okay, only depends on the topology of the diagram. So for example, to leading order in large M, to leading order in large M, then the leading order will be given by the planar diagrams, because that should be the diagrams with h equal to 0, because h is non-negative. So the leading term is given by h0. So all the planar diagrams in this limit, in this so-called 't Hooft limit, will have n dependence, which is n squared. Okay? N squared. So now if you go back to your notes about the 4 diagram we studied last time, about the 2 planar diagram we studied last time, you can immediately tell that indeed it's n squared, okay, in this limit. Yeah. And then you still have an expansion in terms of lambda. So you can do Feynman diagrams, etc. Say lambda just depends on the number of loops. Say if you have one loop, then started with a lambda equal to 0, started with some constant. If you have 2 loops, then lambda, 3 loop, lambda square, etc. Okay? So this is the sum of all planar diagrams, we have this structure. 1 second. So you can imagine you can sum all of this if you are powerful enough, and then you can write it as n squared, then some function of lambda. Okay? So the planar diagram would be just n squared times some function of lambda. So if you are powerful enough to compute this f0 lambda exactly, then you can say you have solved the large n limit of this theory. Unfortunately, for long-abelian gauge theory, we cannot do that. We don't know how to compute this thing. We can only compute perturbatively, which actually does not work for QCD. Okay? Yes?
But n is going to be infinite. I mean, it just seems like, why does this overcome the same problem that we had before?
No, because there's a specific power. Here, there's no specific power. That f can be as large as you want.
But wasn't the other problem also that n was going to infinity? I mean,
No, that's another problem, because here there's a specific limit when you take n go to infinity. In there's no specific limit. There's no limit when you take n go to infinity.
the limit is infinity, right?
No, the limit is n squared. I can say, so this is your essentially your vacuum energy, right? I can say E0 divided by n squared has a well-defined limit.
Okay, sure. Fine.
So the key is that there's a specific dependence on n, but there is unbounded. Yeah.
But I guess another question is, we didn't assume that lambda is a small parameter.
No, we did not assume lambda.
So isn't this kind of perturbative analysis saying that series converges to some function? Is that okay?
It's a very good question, and it is okay. But the reason is more complicated. The key is the following. What I'm writing here, you can understand using 2 perspectives. Just one is heuristic. Just one, say, suppose you can only do perturbation theory, and that would be the thing you compute. And say, if you are powerful enough to solve the theory non-perturbatively, then you are guaranteed just to find some general functions. Yeah, but whether this series actually converges is an important mathematical question, of course, one have to answer. It turns out actually this is convergent. You can mathematically prove this is convergent for very simple reasons. Yeah, this is a side remark, but let me mention it because this is a cool fact. Say if you do just lambda G54 theory, just to the standard Feynman diagram calculation in perturbation theory, the series is divergent. Even no matter how g is small, just the radius of convergence is 0 for any non-zero value of g. Yeah, just the radius of convergence is 0 in terms of g, no matter how small g is. The reason it is divergent is because the number of diagrams, so when you go to nth order, increase exponentially in n. So the coefficient of g, say to the power n, the coefficient can become huge. Yeah, because the number of diagrams increase exponentially in n. So you essentially have g to the power n times n factorial, something like that. And that series is not convergent. But the thing is convergent here, because if you consider the planar diagram, the number of planar diagram is very, very small. Only increase with n as a power of n rather than as a factorial of n. And so you can make lambda small enough, then this can be convergent. Yeah. Right.
Didn't we already see at the end of the last lecture that only planar diagrams give the biggest contribution? So why did we have to go through all this?
Sorry?
And already at the end of last lecture we saw that.
No, not necessarily. That's only for that two diagrams. If you look at this thing, I can draw arbitrarily complicated non-planar diagrams with very large f. It only depends on f. It does not depend on anything else. If you do this, yeah. Okay, so in general, then of course, if you include the higher non-planar diagram, etc., so in general, the vacuum energy, which we normally call log z, okay, log z is the, yeah, essentially is the sum of all vacuum diagrams. So d is the partition function. So it's a path integral. So log z, then we'll have the expansion from h equal to 0 to infinity, n to the power 2 minus 2h f h lambda. Okay, so at each genus level, you will have some function of lambda. Okay. So yeah, the leading order we just draw is f0. And then if you, at the torus level, non-planar diagram is order 1. And then for the two genus is f1 over n squared, etc. Okay? So let me just write down z explicitly. Z is the partition function. Is the partition function S phi. Okay. So if you compute this with the right boundary condition, if you compute this path integral with appropriate boundary conditions, then that gives you the vacuum energy. That's the vacuum diagrams. The log z is the sum of all connected vacuum diagrams, I should say. The sum of all connected vacuum diagrams. Yeah. Connected. Yeah, because of, yeah. Okay. Any questions regarding this? Good. Now, there is a heuristic way. Now there's a heuristic way we can understand this expansion. Okay? So it's actually a heuristic way to understand this one over n expansion. So let's just look at this path integral. Okay? So let's look at the Lagrangian. So Lagrangian I wrote there. In this 2 hoof limit, I can write it as minus n divided by lambda. So I want to write things in terms of lambda. So I multiply in the prefactor n downstairs and n upstairs. So g squared n gives me lambda. And then I have trace, etc. Okay? So now it's easy to see that to leading order, this thing should give you order n squared, because there's already a factor of n here, and the trace is the sum of n things. Okay? So generically, this should be of n order n squared. So now with a little bit leap of faith, say suppose in the large n limit, since your the leading order is order n squared, you can argue that actually order n squared is the expansion parameter if you do saddle point approximation, and then naturally you will see the power will be given by 1 over n squared. Okay. 1 over n squared. Any questions regarding this? Yes?
Can you please repeat what is n over lambda prefactor thing?
Okay, good. So clearly this discussion actually does not. So when I say clearly here, requires a little bit of practice. But clearly, our discussion only depends on the matrix nature of the Lagrangian and the fields. Okay? So now I'm going to make a claim. Is that for any Lagrangian, of matrix valued fields of the form so L, which is n times some coupling divided by some coupling constant times the trace of something. Doesn't matter what you put inside the trace here. As far as you have a single trace, such a theory will always have expansion like this. Okay. We always have expansion. We always have things like this. So let me just summarize. In the 't Hooft limit, in the 't Hooft limit, by 't Hooft limit I always mean this form. The coupling constant is defined. The coupling constant is defined such that you have some coupling constant here, and then you have over m factor, and then of course you can also have some coupling constant inside here. It doesn't matter, as far as those coupling constants are independent of n, and as far as things inside the trace are independent of n. So for such kind of theory, the 1 over n expansion is equal to the topological expansion is the expansion in terms topology of Feynman diagrams. Okay. So this is a very, very beautiful and satisfying result, because in principle, it puts a very simple structure into something in principle is very complicated. Yeah. Any questions regarding this? Yes?
Yeah, maybe it's not. But can I just understand it in such a way that he kind of treat the Feynman diagram as a kind of triangulation of different spaces?
Yes.
Is that the S?
Yeah. For example, you can think of from that point. So we use that to derive, to use this formula, right? Yeah, and that picture will be very useful in a little bit from now on. Keep that picture in mind. The Feynman diagram is like it's like the partition of some surfaces, okay? And that will be very useful later.
Does there ever arise a situation in which you care not about two surfaces, but like Feynman diagrams on three surfaces or something like that? Like, I mean, because this sort of asks the question, you don't necessarily have to consider the topology of two surfaces. I mean, are there any situations in which it's more complicated?
Yeah, but we always draw Feynman diagrams on the paper, which is a two-dimensional.
Sure.
Yeah, it just is enough. 2 dimensions enough. You don't need to go to 3 dimensions.
Okay.
Yeah, and this structure only comes when you go to 2 dimension, because if you go to 3 dimension, of course they don't cross. You cannot talk about in 3 dimension. You can no longer distinguish a planar or non-planar diagram.
Right, but if you did, okay, well, anyway. Okay.
Yeah.
But still, they are not classical.
I know. Okay.
Good. Any other questions? Yes.
And why is always original surfaces? Why is always original?
That's a good question. It's because those lines are orientable. Because when we draw this double rotation, so you have this 2 double rotation. Yeah. So essentially, those lines are orientable. They have a direction, and essentially this is corresponding to so those Feynman diagrams actually have a direction, have a sense of orientation, and so I'm going to mention by passing later, but let me just mention also now. So if you consider, say if the symmetry, if it's not Hermitian matrix, say if it's a real symmetric matrix, and then there's no difference between 2 index, and then there's no orientation, and then that will be related to non-orientable surfaces, and then you need to slightly generalize this. Yeah. Any other questions?
You mentioned that it has something to do with string theory, but that has anything to do with string scattering amplitude.
Yeah, so we were going to talk about that.
They are the same thing?
No, we are going to talk about that. Good. So now let me talk about general observables. Yeah, I think we're a little bit short on time if we want to reach the punchline today. So right now we only have look at the vacuum diagrams, okay? So now let's look at the general observables. Before talking about general observables, let me just again make a side remark, which is the gauge versus global symmetries. So in the example we talk about here, let me call this A, call this equation A, and then let me write down another equation B, which is a Yang-Mills theory. Okay. So the difference between A and B, so the A is this guy. So the difference between A and B is that A, as we discussed last time, is invariant on the global symmetry. Is that there's a UN global symmetry. is that the ux is that phi is invariant under the acting of a unitary matrix, but this u must be constant, okay? Only for constant u, this is a symmetry. But if you have studied a little bit gauge theory, or if you have not studied gauge theory, just take my word for it. The B is invariant under a local symmetry, a local UN symmetry. He said A mu, so A mu is what make up the F u x, A mu x, u dagger x, say minus I partial mu u x. It doesn't matter. The only thing I want to say is that this is ux is arbitrary, can have arbitrary x space-time dependence. Okay, just like the generalization of the QED, it's a gauge symmetry. So the key difference between the two, for example, are also in the key difference between this local and global symmetry are manifest in the what kind of observables we consider. Okay? For example, for A,
I think that should be U dagger. Partial U and then U dagger.
Yeah, that's right. Good. So the difference between, and so this difference, you can say, what's the big deal? In one case, this is constant. This is a dependent on space-time. So the key difference between them is that in the case for A, operator like this, phi square, okay, phi is a matrix, so phi square is a matrix. Phi square x is a allowed operator. Okay, it's an allowed operator. So this operator is not invariant under this global UN symmetry, but it doesn't matter because this is a global symmetry. So this is an allowed operator. But if you have a gauge symmetry, then all operators must be gauge invariant. Okay? Means that all operators must be invariant under this kind of transformations. Say the analog of these is the analog of these are not allowed operators. Okay, so the observables in the gauge theory is much more limited. Okay, so we will be interested in gauge theories. Okay, we will be interested in gauge theories. So that means we will always interested in observables which are invariant under the symmetry. Okay. So we are interested in gauge theories. So that means we are always interested in gauge invariant operators. And so the kind of Lagrangian does not matter. So you can have the gauge field. You can also have some other field, say some matrix phi, etc. As far as the Lagrangian is of this form, okay, it's okay. We always only consider Lagrangian of that form. But you can have arbitrary, say, number of fields and with arbitrary kind of interactions. Okay. Okay, so in such a theory, then allowed. So let's, for simplicity, let's consider local operators. Then in this kind of theory, then allowed, say, local operators must always have some kind of trace in it. Say, you must have the form trace f mu, or trace phi square, etc. Okay? Or trace phi to some power fn, phi to some power of k, etc. You can also have operators with more than one trace, say trace phi square, trace, say f mu, etc. Okay. So we are going to make a distinction. We call the operator with only a single trace, we call them single trace operator. And the operator with more than one trace, we call them multiple trace operator. Okay. So the reason for this distinction will be clear soon. Okay. So multiple trace operator, it's self-evident, again, self-evident that the multiple trace operator can always be written as product of single trace operators. Okay? So let me.
I have a question. This is the only possible case to have a local, gauge invariant operator that f nu times f nu.
Yeah. I always consider local gauge invariant operators. We consider gauge theories. Yeah.
So this combination f nu times f nu is only.
No, this is gauge invariant.
Okay. The only gauge invariant component that we can use.
Sorry?
It's the only gauge invariant component we can use to construct the gauge invariant local operators.
Sorry, I don't quite understand what you mean.
Okay.
No, this is just one specific operator.
Do you have any?
No, you can take f to the power n, an arbitrary number of f. As far as they are inside the trace, it's always gauge invariant.
I see it.
Yeah. Yeah, I'm just writing down a particular example. So just for notational simplicity, I will just write. So from now on, I will just denote the single trace operator. Single trace operators collectively just as O with some script n, which denote the different operators. Okay, so n denote different operators. And then the multiple trace operator, then you have O1, O2, then will be a double trace operator, and O1, O2, O3, say times O3 would be a triple trace operators, etc. Okay?
What is index n?
And just label different operators. Yeah, I'm using an abstract notation. And the reason for this, a distinction will be clear soon. Then for such a gauge series, the general observables in the quantum field theory is just correlation functions of gauge invariant operators. Okay. Okay, just gauge invariant operators. So by gauge invariant operators, you can have local operator, non-local operator, etc. Yeah. So for simplicity, I will restrict my discussion only on the local operators. But local operators means that the fields evaluate at a single point. Okay. So the typical correlation functions, then the typical observable will have this form. will be just product of some correlation functions, a product of some operators, and say their correlation functions. Okay. By C, I mean the connected correlation functions. So you can see immediately, since multi-trace operator are just the product of the simple trace operator, and the correlation function of multiple trace operator can be obtained from those of single trace one, you just identify some of the x, then that will be enough. Okay? And so we only need to talk about the correlation function of single trace operators. So another question, let me call this equation 1. Another question, follow what we discussed before, is how do we decide the independence of this guy? So previously we determined the independence of this vacuum diagrams of this partition function. But now what should be the independence of general correlation functions? Okay. So one way to do it, you just start immediately calculating, and then you can find some rules, etc. But actually, there's a very simple trick. There's a very simple trick to determine the independence of this. So now I will explain. Now I will tell you. So I will not give you any examples because this trick is so nice, and it just works very easily. So, yeah. So the question: what is independence? Of 1. Okay, so this is the question we want to address. So here is a very simple, beautiful trick. So let's consider the following generating functional. So in quantum field series, when we talk about correlation functions, it's always convenient to talk about generating functionals. So whatever is your field, you do the path integral of all fields. And then you look at the action. So you have your original action, which I call S0. And then let's add those operators, JIX, OIX, okay? Yeah, so this is a standard story. When you take derivative over JI, then you will bring down a factor of OI, then that essentially gives you the correlation function. Okay, for example, the correlation function, the connected correlation function of n, the connected correlation function would be just you take derivative of log z, and then delta J1 x delta Jn x8 xn. And then you set j equal to 0, then set all the j equal to 0. Then that gives you the endpoint function. Okay, I should write I here. So I to the power n. Okay. So now, here is the beautiful trick. You can determine just in a single shot the independence of this guy. Okay? And this simple trick is just to add n here. You add n here. In order to get the correlation function, we need to divide it by n to the power n, because now in order to get OI, you need to take derivative of n times ji. So you also need to divide it by 1 over n. But why does this help? Why does this help? It helps for the following reason. Let me call this whole thing as IS effective. Okay? IS effective. So the key thing is that with OI, single trace operators, single trace, okay, then this S effective then has the form n times the trace something, okay? Because your original S0, which is our starting point, have this form, and now the term you added in precisely also have this form. It's an n factor times something single trace. Okay? Okay, something single trace. So that means the whole thing still have this form. Then now we can immediately conclude this log z, say J1, Jn, must have this expansion h from 0 to infinity n to the 2 minus 2h fh lambda J1, etc. Okay? So adding that n is a powerful trick. So now you can immediately, just from here, so we can now immediately find out that for n-point function, connected n-point function, the leading order is 2 minus n. Because the leading order is n squared, it's 2 minus n, and then surprised by 1 over n squared, etc. Okay? Okay? Good? So for example, if you look at the 0-point function, which is essentially the partition function, so this is order n squared, so this is what we found before to leading order. Okay? And if you look at the 1-point function, some operator, then will be order n. If you look at the 2-point function, connected 2-point function of some operator, that will be order 1. And the 3-point function of some operator will be order 1 over n at the leading order. And then all higher order just down by 1 over n squared compared to the leading order. And again, the leading order is given by the planar diagrams, because the leading order contribution to here, in terms of this S effective, is planar diagrams. And then there must be, and those things just obtained by throw away external lag, so they must be planar diagrams. Okay? So again, this comes from planar diagrams. Good. So now let's talk about the physical implication of this. So what does this mean? Okay. So we have found out that this is our n-dependence for our gauge invariant operators. Okay. So what does this mean? Now let me talk about physical implications.
What if one of those O(n) operators had like G inside? What if one of those?
Yeah, you define them without G.
Then something like else is supposed.
Yeah, you define some. So you define something. So when you write down your theory, you define this to hold the limit. Then everything is already in terms of lambda or some other order 1 number. So that can depend on those numbers in the arbitrary way. It doesn't matter. It can depend on coupling count in the arbitrary way, but it cannot have independence defined inside the operator. Yeah, once we introduce this to hold the limit, then the operator can depend on the coupling in the to hold the limit in the arbitrary way. because they are all just order 1 constant. Yeah. Okay, let's talk about physical implications of this. It turns out this seemingly naive behavior actually have a very simple physical picture behind it. Okay, so first is that in the large n limit. So let's just look at the leading order behavior. So in the large n limit, that if we consider this state of OIX acting on the vacuum, okay, so some single trace operator acting on the vacuum. So I again just label different different operators. This can be interpreted as creating a single particle state. Okay. I'm first describing the conclusion, then I will explain why. So if you consider the state obtained by adding a single trace operator on the vacuum, then this can be interpreted as a single trace, a single particle state. So if you act on a double trace operator on the vacuum, then this can be interpreted as a 2-particle state. Similarly, say ON acting on the vacuum would be like n-particle states. Okay. Now, why this is so? Why this is so? So I will support this statement using 3 arguments. Okay. First, remember OI, OJ, the connected Green function of any 2 operators are of order 1. Okay. So we can actually just diagonalize them. You can just diagonalize them. So that OI, OJ, say, proportional to delta ij. Okay. So in some sense, at 2-point function level, those operators can be considered as independent. Okay. And now the second statement. So if you want to call this single particle, this 2-particle, multi-particle, then it should be that they don't overlap, because a single particle cannot overlap with 2 particles, etc. And then to see the overlap between a single particle with a multi-particle, you look at these correlation functions. So if you look at the overlap of a single particle state with a 2-particle state, say some double trace operator. Yeah, let me just, to avoid confusion, let me just use the inside, use this notation to talk about the, to see this as a single operator. Okay? So if you consider the overlap with this single trace operator with this double trace operator, and this double trace this whole thing is like a 3-point function. Okay, you just put these 2 operators at the same point. So from our discussion here, such a connected Green function is of order 1 over n. So this goes to 0 compared to the to this overlap with itself. Okay. So that means in the n goes to infinity limit, there's no mixing between what we call the single particle state, single trace, and the multiple trace state. Okay. The third thing is that now let's look at the 2-point function of two double trace operator, say O1, O2, x, say O1, O2, and y. Okay, double trace operator. Say let's look at the 2-point function of double trace operator. So now there's a leading contribution to this. So let's include all diagrams also disconnected or connected. So leading order is a disconnected diagram, which is essentially O1x, O1y, and O2x and O2y, because I have diagonalized them. Okay, because I have diagonalized them. And then plus the connected Green functions, which is order 1 over n squared. Okay? So if you see this leading order contribution, it's just like two independent particle propagating. Okay, just like the product of two independent propagators. So it's sensible to interpret this as just the propagating of two particles. Okay, so it's sensible to interpret this two particle state, this double trace operator as just creating some two particle states. Yeah, again, this goes to 0 in the large n limit. Okay. So I should emphasize, when we call this a single particle state, it's not necessary they really exist on shell particle corresponding to this state. We are just saying that the behavior of this state can be interpreted as some kind of single particles. Okay, it's just the behavior you can just interpret as single particles. It's not really necessary they exist as stable on-shell particles. In certain cases, there might be on-shell particles, actually stable on-shell particles associated with this kind of state, but for this interpretation to be true, it does not have to be. So in QCD, actually sometimes such a state exists. So we call them global state. Okay, for example, in QCD, the analog of this kind of operator can create some state which they're short-lived, they're not long-lived. They could decay, and so they're typically called global state. So from now on, we just call them globals. Okay, just call them globals. So this is the first implication. The first implication is that just a single particles, a single trace operator can be interpreted as create single particle states, and the multiple trace operator can be interpreted as create multi-particle states. And now the second is that if these global operators, so fluctuations of globals suppressed. Okay? So let me explain what this means. So let me suppose some single trace operator O, which have a non-zero expectation value. Okay? Suppose some state have non-zero expectation value. And then let's look at the variance of this operator, the variance of this expectation value, which is just given by O square minus O square, so the fluctuation, okay? And this is by definition just a collected Green function of O square. Okay, this is the full the full O square. This is the a disconnected one. So this is just a collected part of the O square. And this from Nagier independence, we know this is order 1, order n to the power 0. Okay? So that means, but this below is order n. It's order n. Prove that. So the variance of this compared to the expectation value of this operator itself is suppressed in the Nagier limit. So essentially, in the Nagier limit, so that means the variance divided by operator itself is 1 over n, which goes to 0 in the Nagier limit. Okay? So similarly, if you have a 2-point function, say suppose each 2-point function, so each O1, O2 have non-zero expectation value, then you can factorize this O1, O2 plus O1, O2. So this is disconnected part. And again, this will be of order 1. But this part is of order n squared. Okay? So essentially, the disconnected part always factorize. So disconnected part always factorize. Yeah, it's just like just connected part is always small compared to disconnected part. So this is like a classical theory. Like a classical theory.
We can just 5 minutes. We can proceed if it's 5 minutes.
Yeah, but it may go to 10 minutes. It's just hard to say. It's just hard to say. Yeah, let me do it next time.